In the name of God, hello dear students, my name is Masood, I'm a physics teacher. I want to welcome you to Farhwa's website. Also, we have an application by this name. You can download it on your cell phone to follow our videos. So far, we talked about two sections from chapter 1. And in this lecture, we are going to explain the last section from chapter 1. The title of this section is section 1.3, causes of circular motion. And the first subject of this section is force that maintains circular motion. We denote this force by F sub C, or centripetal force. So simply we can say force that maintains circular motion means centripetal force. Actually, for any moving object in a circular track, there should be a force to maintain the object in a circular track. The force is essential to keep the subject, let's say, circle the circular track, right? This force is called centripetal force, right? Centripetal force can be, any force can be a centripetal force. For example, friction between the car's tire and the road can be a centripetal force for maintaining the car in a circular track. Let's say one more example. Gravitational force between, let's say, moon and earth, right? Can be a centripetal force for maintaining the moon, let's say, in its orbit about the earth. And we have plenty of examples that, let's say, that mentions the centripetal force. So in any situation, centripetal force, let's say, can be a particular force. So centripetal force is not a certain type of force. It's a general, let's say, general conception of forces that maintain circular motion. One more example. For example, I have this, let's say, this simple system. There's a string, the ball tied to a string. I'm gonna, let's say, circle it in a horizontal circle, right? In this situation, I have a question for you. Is there any force that, let's say, that maintains the ball in a circular track? I mean, let's say, is there centripetal force dedicated for the ball to maintain its circular track? The answer is yes, yeah, right? So there should be a force for, let's say, for maintaining the ball in a circular track. This force is called centripetal force, but which force particularly determines the centripetal force here, right? Which force represents the centripetal force? In this example, I can say the tension, the force of tension of the string, let's say, represents the centripetal force. So if you think about my examples, let's say I gave you 3 examples, and in each situation, a particular force, a certain type of force, let's say, represents a centripetal force. So centripetal force is a general concept, is a big set. Any force, let's say, can be a centripetal force, and that's why keep in mind that centripetal force is it's a concept, right? It's a concept. Let's say it's a big set that include all types of forces, right? This is an introduction about centripetal force. Let's dive in with the lesson, and the first, let's say, first thing that I want to, let's say, tell you about the force is the definition of centripetal force. So I defined it like this: any force exerted on a moving object along a circular track that makes the object follow the circular path. So I said any force exerted on a moving object, whether the force is force of tension, whether the force is a gravity, whether the force is uh, any type of force, actually, whether the force is friction or any type of force. Actually, these forces can make, let's say, can make a role of centripetal force. These forces represent centripetal force. So this is the force that, let's say, that is necessary for maintaining the object in a circular track, right? Example, consider a ball tied to a string that is being whirled in a horizontal circular path with a constant speed, right? With a constant, as shown in the figure, like this. And I showed it to you in a simple experiment. In this situation, as a result, so we have some, let's say, outcomes here. What are the outcomes for this, let's say, example? Let me explain it for you. I want to break it down for you. So in the case of this, let's say, example, you have an example. A ball is tied to a string and is whirled in a horizontal circular track, right? So in this situation, force of tension of a string becomes a centripetal force, and let's say, as its name actually, let's say, tells us, centripetal force directed toward the radial direction. It's directed toward the center of a, let's say, circle. It's clear from its name, Fc, centripetal force. And if you let me jog your memory about the information in the previous section, especially, I'm gonna, let's say, jog your memory about this, let's say, this quantity AC. Do you know what AC is? Of course, you know AC is centripetal force. And in previous lecture, in previous lesson, I told you that the AC, we got this information that the AC is directed toward the center. And right now I say FC is directed toward the center. So teacher, does AC have to do with FC or not? Yes. FC, or centripetal force, is the source of AC. I can say centripetal acceleration is due to FC. Centripetal acceleration is due to the centripetal force, right? Let's say, based on Newton's second law, for any motion there should be a force, right? Based on the Newton's second law says that force, any external force, can cause an acceleration for any moving object. So what does it mean? It means F is equal to ma. I mean, acceleration is due to the force. But here, particularly, we have, let's say, we have centripetal force. So the acceleration must be centripetal acceleration, right? So the source of centripetal acceleration is this centripetal force, right? Let me let me read the notes, and I have more, let's say, information about this phenomenon. We are not done yet, actually. I want to add my notes to these tips, actually. But right now, I'm going to read the tip for you. After that, we'll come back to the phenomenon, and I break it down for you. Let's say the first one. It says the ball experiences a centripetal acceleration due to a centripetal force. Yeah, I explained it for you based on the Newton's second law. So the ball undergoes a centripetal acceleration due to the centripetal force. 2, according to Newton's second law of motion, Fc is equal to mac, right? Number 3, both of Fc and AC are directed toward the radial direction. I told you radial comes from radius. Radial direction means to the center, right? Points to the center. That's why think about these vectors, FC and AC. FC and AC are in the same direction. And I can say, if I want you to distinguish, for example, if someone wants us to let's say uh, to separate AC from AC from FC, we cannot separate them because they overlap one another, because they are parallel to one another. That's why they are parallel to one another. If you say, let's say, centripetal force and centripetal acceleration are directed toward the radial direction, they are directed toward the center of a circular track, means they are vectors that these vectors are parallel to one another and they overlap one another. You cannot distinguish, let's say, one from the other. This is the third, let's say, consequence of this phenomenon. Number four, inertia of the ball. It's very important. Inertia of the ball. Actually, inertia is not new information for us. It's a background for us. But here, in this phenomenon, it needs to, let's say, elaborate. Actually, I want to elaborate inertia for you. Let me read the note, and after that, I'll explain for you. Inertia of the ball tends to maintain the ball's motion in a straight line path. So inertia tends to, let's say, tends to maintain the ball in a straight line path. Teacher, what does it mean? The object moves in a circle. So how, let's say, what's the role of inertia here? How does inertia, let's say, tend to move the object in a straight path, in a straight line path? Let me explain for you. Actually, in this situation, whenever you, let's say, whirl the ball in a circular track, whether you whirl it vertically or horizontally, no problem, it doesn't matter. In this situation, actually, in these situations, I can say two things are competed with one another. Two, let's say, quantities are vied with one another. What are the quantities that compete with one another in this phenomenon? Centripetal force versus inertia. Centripetal force, as I explained it for you, tend to keep the object in a circular track. Centripetal force is a force that maintains the object in a circular track. You know this. But what's the role of inertia? Actually, inertia stands against the centripetal force. Inertia tends to, let's say, throw out the object from a circular track. It tends to eject the ball, right? It tends to eject the ball from the circular track. That's why we say that the inertia tends to, let's say, maintain the object in a straight line path. Inertia of the ball actually tends to eject the ball from a circular track. It tends to throw the ball out of the circular track. That's why, let's say, in this situation, two, let's say, quantities compete with one another. For example, let me break it down for you. If centripetal force overcomes the inertia, what does it mean? So centripetal force wins the battle. Centripetal force wins the race. It is the winner. Centripetal force is the winner. That's why the ball, let's say, maintains in its circular track. In this situation, ball maintains in its circular track because centripetal force controls the situation. Right? Is there another case? Yes. Teacher, what happens if the inertia overcomes the centripetal force? Good question, right? Sometimes inertia, let's say, overcomes the centripetal force. In which situation? When the, let's say, when the string breaks. When the string breaks, automatically centripetal force becomes zero. Centripetal force vanishes. It disappears, right? And in this situation, inertia controls the situation, and inertia, let's say, uh, gives the ball tangential velocity, like this figure actually, this tangential velocity is due to what? Is due to the inertia. Is due to the inertia of the ball. But here, let's say the amount of centripetal force is more than the amount of inertia. That's why it's the ball keeps moving in a circular track, right? And I told you in a situation when the string breaks, in that situation, inertia controls the situation. Inertia, let's say, gives the ball tangential velocity. Inertia, let's say, uh, um, tends to eject the ball from a circular track. That's why keep in mind that these, let's say, these quantities compete with one another. Sometimes, let's say, one of them overcomes the other. And I'm gonna, let's say, summarize it for you for better understanding. Let me, let's say, write it here. The first situation, when centripetal force overcomes the inertia, right? Inertia. What's the consequence of this situation? What happens? The ball or the object, let's say object, the moving object, let's say maintains in a circular track. Maintains in a circular track, right? This is about the, for example, first case. What's the second, let's say case? The second case, when inertia overcomes the centripetal force. The opposite situation, when opposite situation happens, inertia in this situation, right, overcomes the FC. And I told you, I gave you an example. When the string breaks, inertia controls the situation. It overcomes the FC because FC, let's say, does not remain anymore. When the string breaks, FC automatically becomes zero. It vanishes, it disappears. And in this situation, inertia, let's say, gives the object, gives the ball tangential velocity. And the object in this situation, let me write it for you. Object, let's say, ejects, right? Object is ejected, let's say. Object is ejected by means of inertia. Object is ejected. Object throws away from a circular track. Object throws out from the circular track by means of what? By means of inertia, right? So this is about the inertia. I'm sure you have, let's say, an idea about inertia right now. And you know that in any, let's say, circular track for any moving object, two phenomenon or two quantities compete with one another. What are these quantities? Centripetal force versus inertia. Let me read another note for you. So we have sixth note here. Let me read the fifth one because let's say I read the fourth one. It was about inertia. Right now, I'm gonna explain the fifth one. The string exerts a tension. You see, so the type of, let's say, the string exerts a tension. So which force existed? Which force is existed within the string? Let's say tension. Tension becomes a centripetal force in this case. So the string exerts a tension force on the ball to follow a circular path. So can I say tension here, let's say, represents a centripetal force? Can I say tension is a force that maintains circular motion for the ball? Of course, tension here in this situation is centripetal force. And the last one, the centripetal force is the force that maintains circular motion. It's a simple definition for centripetal force. And let me add one more note for you about the centripetal force. And let's say I'll write these notes actually in maybe in next page. I'll show it to you actually, but let me explain it in advance for you. And centripetal force, I can say centripetal force about the, let's say, is, this is the sixth let's say note, that centripetal is the force that maintains circular motion. Yeah, the last one, and I want to, let's say, add this note here actually. Centripetal force, I can say, is a force that, excuse me, let me think about the note. It's very important here, but yeah, centripetal force is a net force. Yeah, I'm sorry about that. I forgot, let's say, the word. Centripetal force is a net force, or I can say it's the resultant force. What's the meaning of net force or resultant force in physics? Any force, let's say, uh, net force means more than one force, right? Whenever you want to let's say, whenever you want to define the centripetal force, you can say it's the net force, right? It's a net force on an object, right? That keeps the object in a circular track, right? So net force means there's more than one force. What does it mean? Sometimes, in some situation, and I can say mostly centripetal force is more than one force. That's why it's a resultant force. It's a summation of, let's say, two or three forces that all together make a centripetal force, right? So centripetal force is a net force, is a resultant force. Let me give you an example to better understand this subject. For example, think about a passenger, let's say, in a car, right? There's a passenger in a car. This let's say this person actually wears a seatbelt. He or she wears a seatbelt. So seatbelt here becomes a part of centripetal force. Tension of a seatbelt becomes a part of centripetal force, and the other, let's say, force that helps the centripetal force and belongs to centripetal force is the friction between the body of a person and the seat, right? Let's say the friction between the two surfaces, between the seat of a car, between the car seat and let's say, and the body of a person. So I mentioned two forces. I mentioned uh, tension of the seat belt and the friction between the let's say, body of a person and the car seat. So in this situation, I can say these forces, friction plus let's say tension, become centripetal force. That's why we say centripetal force is a net force, or is a resultant force that keeps the object in a circular track, right? Uh, that was the note. Uh, let's say I'll include it for you in the next page, but I wanted to let's say, to tell you in advance. Right now we have a table here. The title of table is Common Rule of Centripetal Force. Common rule of centripetal force. What's the common rule of centripetal force? Let me explain it for you. Let me show it to you. This is their first table. It's about the so common rule of centripetal force. These actually rules are very common. I can say they are original rule for centripetal force. The first one, Fc is equal to mac. This is the Newton's second law of motion, application of Newton's second law of motion for centripetal force, right? Fc is equal to mac is used to figure out Fc. This is the first one. Number two, AC is equal to Fc over m. So where does this rule come from? I want you to rearrange the equation. AC is unknown. So any, let's say, any variable multiplied by AC goes to the denominator and FC goes to the numerator. That's why AC is equal to FC over M. Is used to figure out AC. M, right now, M is unknown, right? When you are asked to find M in a question, right, you have to rearrange the equation. M becomes FC over AC. Is used to find M. So this is about the common rule in general. We have one more table. Let me show it to you actually. Rules related to centripetal force. What are the rules that related to centripetal force? Let me, let's say prepared it in this table. The left part of the table is dedicated for what? For the rules that include mass, tangential speed, and R. Or I can say a linear or tangential information. The first one, F is equal to mvt squared over R. Teacher, where does this rule come from? I'll prove it for you at the end of this, let's say, lesson. I'll prove it for you. F is equal to mvt squared over R is used to figure out Fc. Right now, just let's say take a look at these rules. After that, I prove it for you at the end of this lesson. Number two, Vt is equal to, let's say, from this rule, right? Figure out Vt. Rearrange the rule for Vt. Because Vt is squared, that's why the rule, let's say, is located under the square root. So we have a square root of what? Square root of Rfc divided by M. Because M is a coefficient of Vt, that's why it goes down. This rule is used for finding Vt. The third rule, R is equal to mvt squared over Fc, right? R. Right now, we want to rearrange the equation for R. If you cross multiply the rule, actually, Fc multiplied by R, that's why Fc goes down, and mvt squared goes to the numerator. And the last rule, we want to figure out M. We want to rearrange the rules for M, which, let's say, quantity multiplied by M, Vt squared goes down, and Rfc goes up, actually, is used to find M. I want you to memorize these rules. So the left part was dedicated for what? The left part was dedicated for linear or tangential information. The right part, let's say, is dedicated for what? Dedicated for the rule of Fc that include what? That include M, omega, and R. Means mass, angular speed, and radius. So I can say the right part is devoted for the angular information, not linear or tangential information. The first one, F is equal to mr omega square, right? Mr omega square. Let's say, I'll prove it for you in, let's say, at the end of this lecture. F is equal to mr omega square. Omega is equal to, right now I'm gonna, let's say, I'm gonna figure out omega. We are going to find the rule for omega. So omega is unknown. Mr, let's say, Mr is the coefficient of omega. That's why it goes down. Fc goes to the numerator. And the rule, let's say, put under the, let's say, square root, because omega is squared. Whenever you want to remove the exponent, you have to, let's say, you have to put the fraction under the radical, right? Number three, R is equal to, I want you to figure out R, right? R is equal to Fc divided by M omega square. And the last one, figure out M for me, rearrange the equation for M. M is unknown. You have to start from M. M is equal to Fc divided by R omega square. It's used to find M, right? Note number one, we have two notes here after this table. Centripetal force is measured in Newton. Of course, any type of force is measured in Newton. Newton is a unit of centripetal force, or any type of force in SI. Note number 2, centripetal force, or Fc, is not a certain type of force. I explained it for you actually in advance, but it is an expression. It's an expression for the forces that maintain circular motion. So it's just an expression, or it's a general concept, general conception for the forces that maintain circular motion, right? So till now, I explained, let's say we talked about centripetal force in general. We gave some examples. We got some rules. We separated the rules into the tangential and angular, let's say, quantities. Right now, let's keep going. We have note number 3. Any force can be a centripetal force. I explained it for you in advance. For example, so I prepared 2 examples for you here. The first example, gravitational force, right? Gravitational force is the first example. So it says gravitational force is a force that keeps the moon in its orbit around the Earth, right? You see? So this is the moon. Moon circles the Earth in an elliptical orbit, and the orbit of any planet and orbit of any moon about the planets. Orbits are not, let's say, circular. Orbits are elliptical, right? They are oval, elliptical. That's why actually Galileo believed the let's say perfect circular track for the planets about the sun, but Johannes Kepler, I can say, was the first person that let's say that mentioned that the orbit of the planets are not let's say circular. Kepler explained that the Galileo was wrong in this case actually, and the orbits of planets let's say are not circular, they are elliptical. This is let's say Kepler said actually, right? So this is an Earth. This is our globe, right? And the moon circles the Earth. Here in this situation, is there any force, let's say, that maintain, right? That maintain the moon in its orbit, of course? Or I can say, is there any centripetal force to maintain the moon in its orbit about the Earth? Of course. So determine the Fc exactly here. Can I say Fc is equal to Fg here or not? Yes. Fg means gravitational. So gravitational force of Earth, right, becomes a centripetal force for, let's say, for orbiting the moon about the Earth. Fc is equal to Fg, right? This is the first condition. Here, about this example, there's a car. The car circles a defile, actually. There's a defile, or there's a circular track. The car, let's say, moves around the circle. I want you to determine the centripetal force. And firstly, is there any centripetal force? Yes. For any circular track, for any moving object in a circular track, there must be a centripetal force. So centripetal force, determine the centripetal force exactly for this case actually. What force or which centripetal force keeps the car in its orbit, right, about a circular track? Can I say it's Fs or not? Fs, I mean friction, force of friction between the tires, car tires, and the road becomes a centripetal force. So here you see, let's say this is a confirmation of this note. Any type of force, we have a note, let's say note number 3. Any force can be a centripetal force, right? This is the confirmation actually. I can say here in this example about the car actually, the example of car, friction becomes a centripetal force. Example of moon, gravitational force becomes a centripetal force. That's why it's okay for any type of force to be a centripetal force. We have a tip here. What's the tip? Let me read it for you. Fc and Vt are perpendicular to one another. It's very important. And I'm gonna, let's say, explain it for you. Fc, this is Fc, right? This is Fc, and this one is Vt. Which type of relationship is there between Fc and Vt? You see, let me extend the Vt. In this situation, I want you to determine the angle between Vt and Fc because they cut one another. So in this situation, they make a, let's say, right angle. That's why there's a 90-degree between tangential speed and centripetal force. So in other words, I can say they are perpendicular to one another. They are perpendicular to one another. So are these quantities similar to one another? No, they are not similar because this one is a tangential velocity and this one is centripetal force. They are not similar. What do I mean by similar quantity, and what do I mean by, for example, dissimilar quantity or different quantity? Let me, let's say, tell you a note. If you, let's say, confront the, let's say, similar quantities like what? Like a centripetal acceleration, centripetal force, right? They are, let's say, similar quantities. If I say, what's the relationship between centripetal force and centripetal acceleration? Without thinking, you have to say, teacher, they are parallel. Why? Because they are similar. FC, look here, FC and this one is AC. FC and AC are parallel because they are similar. So for any similar quantities like FC and AC, like for example VT and AT, right? The angle between them is 0, means they are parallel. But for any, let's say, for any two different, let's say, quantities like centripetal force and tangential velocity, like this. So FC, VT, are they similar? No. This one is tangential, this one is circular, centripetal. So in this situation, they are not parallel. They cut one another, and the angle between them is, let's say, 90-degree. Right? This is the key for recognizing the angle between them. This is the key to determine the relationship between these quantities. So for similar quantities, keep in mind that always they are parallel. Similar quantities are parallel. And parallel lines means there's a 0 angle between the parallel lines. And for any, let's say, different quantities, the relationship between them is perpendicular. What do I mean by perpendicular? Means the angle between them is 90-degree. That's it. So this is the tip. And the last thing for this lesson, I'm gonna, let's say, I promised you to let's say, to prove this law actually, Fc is equal to mr omega square. Let me prove it for you. And after that, I finished, let's say, this lecture. This is the last thing, this proof actually. By the end of this proof, I finished the lecture. I finished the lesson for you. Proof of equation Fc is equal to mr omega square. We want to prove this equation, right? We start from what? We start from this equation. Fc is equal to m Vt square over r, right? And by the way, before I start actually, let me tell you the origin of this rule, because I promised you to, let's say, to even, let's say, prove this rule. Fc is equal to the origin. The origin of this rule is Newton's second law. I mean, Fc is equal to mac. This is the origin of this rule. Fc is equal to AC becomes VT square over R. This is the origin of this rule. But right now, we want to prove this equation. F is equal to mr omega square. Start from here. F is equal to mvt square over R. And Vt itself is equal to R omega. I want you to substitute the value of Vt here. So it will be F is equal to mr square omega square divided by R. Teacher, can I cancel out R with R? It can be. So Fc becomes mr omega square. Actually, this is the proof of this rule. And thank you very much for watching this video. I hope you enjoyed this lecture, and bye-bye.